These are the answers to the Chapter 8 packet, Basic Concepts of Chemical Bonding. Section 8.1, Lewis symbols and the octet rule. So we know from the information in Table 8.1 on page 290 that when you are placing the dots around the atom representing the valence electrons, you go from 1 to 8, and you can see the pattern that as we typically try to spread those electrons out, once we get past carbon, we end up having a mixture of single dots and lone pairs. So here I am putting the 1, 2, 3, 4 dots around the atom, and then when I get to 5, 6, 7, 8, you've seen those patterns before. The definition of the octet rule, to avoid using the word 8, is that atoms generally tend to gain or lose or share electrons until they are surrounded by a full valence shell. Section 8.2 is on ionic bonding. So we have a crystal lattice, a picture of sodium chloride, and the question is asking, how do we know which ion is sodium and which ion is chloride? Well, remember that sodium, the ion, has 10 electrons, whereas chloride, the ion, has 18 electrons. So sodium should have a smaller ionic radius than chloride. And you can see this in figure 8.3 on page 291. Part B is asking you to draw an arrow to indicate the direction of electron transfer, and we have to fill in the valence electrons on both sides. So sodium should have a single valence electron. Chlorine, the atom, should have 7 valence electrons. Sodium gives up its electron to chlorine to produce the sodium cation and the chloride anion. And again, you'll see this diagram of electron transfer on page 291. Properties of ionic substances are, they are crystalline, they usually have high melting points, they are brittle, and they can be cleaved or broken apart along smooth, flat surfaces. The reason why they break apart along these flat surfaces is because of electrostatic forces. So I had you look on page 481 at figure 12.25, and you can see in the figure that when a stress is applied to an ionic crystal, the planes of atoms slide in response to the stress, and now, like charges, repel each other, which causes the matrix or the crystal to break apart along well-defined planes. We know that the ionization of an atom is always an endothermic process because you are pulling an electron away from an atom and you have to break those attractive forces. But on the other hand, when a chlorine atom gains an electron, it's producing a more stable, so therefore has lower energy, ion. And therefore that's exothermic when chlorine gains an electron. Now if we just combine the two reactions shown above, we might think that the formation of sodium chloride is an endothermic process because positive 496 and minus 349 gives you positive 147. Well, this view is incorrect because this view corresponds to the formation of sodium and chloride ions that are infinitely far apart. In other words, the positive energy change assumes that the ions do not interact with each other. But that's quite different from the situation in ionic solids. There's a very strong interaction between sodium and chlorine. In fact, the principal reason that ionic compounds are stable is the attraction between ions of opposite charge. On page 292, they define lattice energy as the energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. So here we have either an endothermic, so positive 788 kilojoules, or an exothermic, negative 788 kilojoules. So which is which? Well, breaking apart the attractive forces is an endothermic process, but forming the attractive forces between the ions would be an exothermic process. So lattice energy for sodium chloride is 788 kilojoules. Equation 8.4 on page 293 You've already seen that back in chapter 5. It has to do with the potential energy of two interacting charged particles. If we assume that Q1 and Q2 are the charges on the particles and d is the distance between them, and k is just a proportionality constant, then it shows us that when you have oppositely charged ions, the attractive force will increase as the magnitude of the charges increase and as the distance between the ions decreases. So the lattice energy increases as the charge on the ions increase and as their ionic radii decrease. Why would MgO, magnesium oxide, have a higher lattice energy than sodium fluoride? Let's take a look at the sizes of these ions. Now, magnesium is slightly smaller than sodium, but there is not a significant difference between their ionic radii. And oxygen is slightly larger than fluorine, but again, there is not a significant difference between the radii. So is this comparison, is it more about the magnitude of the charges, or is it about the distance between the ions? Well, since the ionic radii are similar, it's about the magnitude of the charges on the ions. So MgO, with its +2 and -2, has a greater magnitude of charge than sodium fluoride with its +1 and -1. So that's the reason why the lattice energy of MgO is greater than that of sodium fluoride. Now we're going to compare why the lattice energy of sodium fluoride is greater than potassium chloride. And so we're comparing ions that both have +1 and -1. So the magnitude of the charges on the ions in sodium fluoride and potassium chloride are the same value. So it must be about the distance between the ions. The ionic radius for sodium is smaller than that of potassium. The ionic radius for fluoride is smaller than that of chloride. So therefore, the distance between the ions in sodium fluoride is less than the distance between the ions in potassium chloride. And again, smaller distance between the ions leads to a greater attractive force between those ions. As we compare lithium chloride, potassium bromide, and magnesium chloride, let's see if we can arrange these three compounds in order of increasing lattice energy from weakest to strongest attractive force. Well, MgCl2 would have a higher lattice energy than LiCl because the charge magnitude on magnesium is greater than that of lithium. And since lithium ions and chloride ions are smaller than those of potassium and bromide, the distance between the ions in LiCl is going to be smaller than that of KBr. So KBr has the weakest attractive forces, followed by lithium chloride, and then finally magnesium chloride. They are arranged in order of increasing lattice energy. Even though lattice energy increases with increasing ionic charge, why do we never see ionic compounds that contain Na2+? Wouldn't 2+ be even better than +1? Well, even though lattice energy increases with increasing ionic charge, we never find ionic compounds that contain sodium 2+ ions because the second electron removed would have to come from an inner shell of the sodium ion, the 2p as opposed to the 3s. And removing electrons from an inner shell, as you learned in chapter 7, requires a very large amount of energy. So the increase in lattice energy from having a +2 charge for sodium is not enough to compensate for the really high energy needed to remove that inner shell electron. So we only see +1 charges for group 1 alkali metals. So now we're going to talk about what's called the Born-Haber cycle, or Haber cycle. And this has to do with several different steps to produce a crystal. You can see it in a closer look on page 295, calculation of lattice energies, the Born-Haber cycle. And this diagram features several steps, the first of which is the sublimation of sodium from a solid to a gas. The second step involves breaking the covalent bond between chlorine atoms in a diatomic molecule. The next step involves the ionization of sodium, so removing an electron. The next step involves the addition of an electron to chlorine, so that's the electron affinity. And then finally, the step that you can see that goes all the way from top to bottom, from Na plus and Cl minus down to NaCl solid, that is the lattice energy that we're talking about. So we're going to use information to calculate the lattice energy. Sublimation of sodium would be going from solid to gas, and that is 108 kilojoules. That's an endothermic process. Another endothermic process is to break the bond between a chlorine atom bonded to itself in a chlorine molecule. So now that's going to be 122 kilojoules. A third endothermic process is to remove the electron from sodium. The gaseous atom loses one electron. That's 496 kilojoules. But our next step is actually exothermic. It's the addition of an electron to a chlorine atom to form a stable chlorine ion. Again, this is still in the gas phase. So now we have to take the gaseous sodium and chloride ions and turn them into solid sodium chloride. Now that energy is defined as the lattice energy. We're going to assume that we don't know that value, and we're going to calculate it using a final equation, which is the heat of formation, the enthalpy of formation for sodium chloride. And that would look like this. Solid sodium plus a half a mole of chlorine gas produces solid sodium chloride. That process releases 411 kilojoules. So how can all 6 of these reactions be used to calculate the lattice energy? Well, if we write all these equations, you can see that the sum of these first 5 equations is equal to the sixth equation. If we cross out the things that are the same on both sides, what we have left is solid sodium plus half a mole of chlorine gas to produce 1 mole of sodium chloride. Now, if that's negative 411 kilojoules for the overall reaction, that means that the sum of the enthalpies of the first 5 reactions have to equal negative 411. So if we add up all these values, 377 kilojoules plus the lattice energy equals negative 411. Solving for lattice energy, we get negative 788 kilojoules. So what does that mean? That when 1 mole of sodium chloride is formed from gaseous ions, it releases 788 kilojoules of energy. You could say it another way. It takes 788 kilojoules to completely separate 1 mole of sodium chloride into gaseous ions. All right, we're still in section 8.2, ionic bonding. The last little bit here is reminding you of things you learned back in chapter 6 and chapter 7. That we always remove electrons from the S subshell before the D subshell for transition metal atoms. So since iron has a configuration which is argon, 4s2, 3d6, the plus 2 charge would be just argon, 3d6. The 4s2 electrons are removed, and then to remove another electron would take the configuration down to argon, 3d5. Section 8.3, covalent bonding. The diagram at right represents the electron distribution in a molecule of hydrogen. So where are the electrons involved in covalent bonding? Well, they're in between the 2 positive nuclei, and that represents the covalent bond. So the atoms in the hydrogen molecule are held together because the 2 positive nuclei are attracted to the concentration of negative charge between them. In writing Lewis structures, we usually show each bonding or shared electron pair as a line, and any non-bonding or unshared electrons as dots. For nitrogen, each nitrogen atom has 5 valence electrons, so we have 10 electrons altogether. We can connect them with a dash. That's 2 electrons. And then we have lone pairs or non-bonding pairs. That would be 4, 6, 8, 10. Now those 10 electrons have not been distributed in a proper way because the nitrogen on the right does not have access to a full octet. If we make not just a double bond, but rather a triple bond, now each nitrogen atom can share a total of 6 electrons between them. And with the lone pair on each atom, there is a full octet for each nitrogen atom. Oxygen, O2, has 12 electrons and is going to be written as a double bond. Fluorine, F2, has 14 electrons and would be drawn with its Lewis structure as a single bond. As a general rule, when you go from a single to a double to a triple, the length of the bond between two atoms is going to decrease as the number of shared electron pairs increases. Now we're into section 8.4, bond polarity and electronegativity. They want you to give examples of the different types of bonds. A nonpolar covalent bond should be between two nonmetals that are the same, because that way there is no difference in electronegativity between the atoms. So the electrons are shared equally. But for a polar covalent bond, they should be two nonmetals and they are different. And whichever atom has a greater electronegativity is going to be attracted more strongly to that pair of electrons. Finally, an ionic bond would be typified by a metal and a nonmetal. So I've given you two examples of that. All right, let's take a look at electronegativity. You can see on page 299 that it's defined as the ability of an atom in a molecule to attract electrons to itself. And you can see that electronegativity generally seems to increase from left to right across a period and decrease from top to bottom down a group. In the top right corner, which is the halogens, you would expect to have an atom with a high value for electronegativity because it has a large negative value for its electron affinity, so it prefers to gain electrons, and it has a high value for first ionization energy, so a strong attraction for electrons, high electronegativity. As I said, in general it tends to increase from left to right and decrease from top to bottom. So why is an FF bond nonpolar and why is an HF bond polar? Well, the FF bond is nonpolar because the two fluorine atoms have the same electronegativity value. There is equal sharing of the electrons in the covalent bond between them. On the other hand, a hydrogen fluoride bond is polar because since fluorine has a higher electronegativity than hydrogen, the electrons are not shared equally. They are more attracted to the fluorine atom than to the hydrogen atom. So each of the following bonds is polar, but we're going to look at the trend in electronegativity to decide which atom is partially positive or partially negative. So looking at hydrogen and oxygen, since oxygen is further to the right and is more electronegative than hydrogen, the hydrogen gets a partial positive charge and the oxygen gets a partial negative. Comparing carbon and nitrogen, nitrogen is more electronegative, so gets a partial negative charge. Comparing iodine and fluorine, electronegativity decreases from top to bottom down a group, so fluorine gets the partial negative charge in that bond. And with silicon and bromine, bromine is several groups over, further to the right. It is more electronegative than silicon. And then finally, comparing arsenic and chlorine, chlorine is closer to the top right corner of the periodic table, so it gets the partial negative charge. It is more electronegative. The greater the difference in electronegativity between two atoms, the more polar their bond is. And if we use an arrow with a crossed end like this to denote a charge separation, the arrow always points toward the atom that has a higher electronegativity value. That is called a dipole when two electrical charges of equal magnitude but opposite sign are separated by a distance. The measure of the magnitude of a dipole is called the dipole moment. We are not going to calculate dipole moments in this class, but we can compare the polarity of different bonds and different molecules and say which one is more polar or less polar. If a molecule is nonpolar, it has a dipole moment of 0. Assuming that bond lengths are fairly constant, we can say that as the electronegativity difference between two atoms increases and the bond becomes more polar, the dipole moment of that bond increases. Even though there is a continuum between the extremes of ionic, where you have a complete transfer of electrons, and covalent, where you have a complete sharing of electrons, there's all kinds of in-between. So it's a simple approach to assume that metals and nonmetals form ionic bonds and that two nonmetals form covalent bonds. And again, the covalent bond might be nonpolar or polar. SnCl4, which is tin chloride, is a colorless liquid. That's not consistent with an ionic bond. It freezes at -33 and boils at 114. That's a very low melting point and boiling point. Also, not consistent with a traditional ionic bond. So therefore, those properties suggest that SnCl4 has covalent properties. Section 8.5, Drawing Lewis Structures. This begins by calculating the total number of valence electrons for the molecule or the ion. So Si, silicon, has 4 valence electrons. Each chlorine has 7 valence electrons, and there are 4 of them. Grand total, 32 electrons. For phosphorus trifluoride, PF3, we have 5 plus 21 is 26. And for sulfur dibromide, SBr2, we have 6 plus 14 is 20. We draw single bonds to connect all of the atoms, and if we have extra lone pairs, we put them around the atoms to fulfill the octet. So these are the Lewis electron dot structures for silicon tetrachloride, phosphorus trifluoride, and sulfur dibromide. Again, you can see that every atom has a full octet, and there are only single bonds in each structure. CH3NH2, which is methylamine, has a skeleton that is going to contain a total of 14 electrons. So we have a lone pair on the nitrogen. Everything else is a single bond. And then we have chloroethane, C2H5Cl, and the only atom that adds a pair of electrons, lone pairs, is the chlorine. Everything else has single bonds. So we have a full octet for both carbons. Each hydrogen has access to 2 electrons, which is a full energy shell. And again, those are fairly straightforward Lewis electron dot structures. Well, what happens if you have double or triple bonds? In this example with carbon, oxygen, and 2 chlorines, we have 24 electrons. With C2H4, we have 12 electrons, and C2H2, we have 10 electrons. I had to make a double bond between the carbon and the oxygen because I didn't have enough electrons to go all the way around. So there's a double bond. C2H4 has a double bond between the carbons, and C2H2 has a triple bond. Again, each atom has either a duet for hydrogen or an octet for things like carbon, chlorine, and oxygen. HCN has 10 electrons. SO2 has 18 electrons. And you can see a triple bond between the carbon and the nitrogen in HCN. And you can see a double bond on one side between sulfur and oxygen in SO2. But each atom does have a full octet. Now, when you have a polyatomic ion, you have to either add electrons if you have a negative charge, or you take away electrons if you have a positive charge. So ClO3 minus has 26 electrons, and its structure looks identical to phosphorus trifluoride, which also had 26 electrons. We do put brackets around the Lewis structure and put the charge on the outside. For NO3, we have 24 electrons because it's a -1 charge, so 5 plus 18 plus 1 more. And that's going to be a double bond between one of the oxygens and the central nitrogen atom. In the case of NO2 plus, we have 5 plus 12, but then take 1 away, we have 16 electrons total. We can make 2 double bonds. That molecule would look similar, that ion looks similar to carbon dioxide, which also has 16 electrons. In the case of sulfate SO4, we have a total of 32 electrons, so single bonds all the way around. And in the case of the carbide ion, which is C2 2-, we have a total of 10 electrons, which means that its structure looks very similar to the nitrogen diatomic molecule that we saw earlier. So earlier I showed you an example of the molecule on the left where there was a double bond between the carbon and the oxygen. But I could have drawn the double bond between the carbon and one of the chlorine atoms. Which of these structures do you think is more likely to contribute to the actual structure of CCl2O? Well, it turns out that based on something called formal charge, if we can draw more than one Lewis structure, which obeys the octet rule, we can use formal charge to decide which structure is the most important. The formal charge of any atom in a molecule or an ion is the charge the atom would have if all of the atoms had the same electronegativity, which means we split the bonding pair equally. So we calculate the formal charge by assigning electrons to the atom. All unshared or non-bonding electrons are just given to the atom wherever they're drawn, but any bond is cut in half. And the formal charge is subtracting the number of electrons assigned from the number of valence electrons. Again, the answer to D is that we're assuming that each bonding pair in the Lewis structure was shared equally, and formal charge is valence electrons minus the electrons assigned to the atom. All right, let's take a look at examples of formal charge. In this case, we have a chlorine which carries 2 non-bonding electrons and then has 3 single bonds. If we cut each single bond in half, this counts as 3 bonding. Again, we had 2 non-bonding, that's 5. So 5 electrons are assigned to chlorine, 7, which is the normal number of valence electrons, minus 5 equals positive 2. Each oxygen has 6 non-bonding, and we cut the bond in half, that's 1. So we have 7 electrons assigned, 6 valence electrons minus 7, negative 1. So we've assigned formal charges to each atom, and if we add up those formal charges, they should equal 0 for a neutral molecule, or they equal the overall charge on the polyatomic ion. In the nitrate ion, we have negative 1 for the single bonded oxygens, we have 0 for the double bonded oxygen, and we have positive 1 for the central nitrogen atom. With this next polyatomic ion, NO2+, the 2 oxygens are 0, and the central nitrogen atom is positive 1. For the sulfate, each oxygen is negative 1, and the sulfur is positive 2. For the carbide ion, C2 2-, we end up with each carbon having a formal charge of negative 1. Note that in both cases, the formal charges either add up to 0 if it's a neutral, or they add up to equal the overall charge of the polyatomic ion. We're trying to get the formal charges as close to 0 as possible, and if there are negative charges, we're trying to put them on the atoms that have a greater electronegativity. So if more than one structure is possible, we try to get formal charges to help us decide which one is dominant. The atoms should have formal charges as close to 0 as we can, and putting negative charges on the more electronegative atoms. So the first structure would be 0, 0, and negative 1. That's, again, 6 minus 6, 4 minus 4, and 5 minus 6. The next structure would be positive 1, 0, and negative 2. That's 6 minus 5, 4 minus 4, and 5 minus 7. And then the final structure would be -1, 0, and 0. Again, that's 6 minus 7, 4 minus 4, and 5 minus 5. So which structure is the most dominant? Well, considering that nitrogen has a greater electronegativity than sulfur or carbon, let's focus on the structure that puts the negative charge on nitrogen as the most dominant. The worst structure would have the greatest magnitude of formal charge, which makes the center one the worst. Here we have a polyatomic ion for which we don't know the overall charge. All we have to do is add up the formal charges of each atom, and that will give us the overall charge of this polyatomic ion. Each oxygen carries a formal charge of -1, except for the center oxygen, which has a formal charge of 0. And the two phosphorus atoms have formal charges of +1. So we add those up and we get a total of -4. So that is the charge on the ion. Remember that formal charges do not represent real charges. They are just a convenient bookkeeping method that helps us decide which structure is preferred. All right, on to section 8.6 entitled Resonance Structures. So based on figure 8.12 on page 309, does the ozone molecule contain one shorter double bond and one longer single bond? Well, the answer is no, because if they did, there would be different bond lengths, and clearly the two OO bonds have the same length. So therefore, the ozone molecule cannot contain one double and one single, because each bond has the same length. We're going to use a double-headed arrow drawn in between two resonance structures. Does that mean that the two forms of the molecule are just rapidly oscillating back and forth? No. Molecules such as ozone cannot be described as oscillating between the two individual Lewis structures. There are two equivalent structures that contribute equally to the actual structure of the molecule. The actual arrangement of the electrons in molecules such as ozone must be considered as a blend of two or more Lewis structures. So how does blue plus yellow equals green help us understand the concept of resonance? Well, just like green paint is a combination of blue and yellow, it does not oscillate back and forth. An ozone molecule does not oscillate back and forth between these two Lewis structures. Each one contributes to the actual structure. But since we can't draw half a bond, that's the best we can do. So what exactly are resonance structures? They have the same arrangement of atoms, but a different arrangement of electrons. If we go with an example for acetate, CH3CO2- has a total of 24 electrons. So there is the skeleton structure for acetate. Do I have 24 electrons? Well, right now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. This is not my final structure because carbon doesn't have an octet, but now I have a choice. I could make the double bond on either oxygen with carbon. So the two resonance forms would look like this, alternating single and double bonds. And the actual structure of acetate would be a hybrid of these two structures. Now we have to draw not two, but three different resonance forms for carbonate. So carbonate CO3 2- has 24 electrons. And if we stop here, we don't have an octet for carbon until we make a double bond. But since I have three different places in which I can draw that double bond, we have three different resonance forms for the carbonate ion. And the average of all three of these structures would be contributing to the overall picture of carbonate. Benzene has two different forms in which there are 6 carbon atoms bonded in a hexagon. 1 hydrogen atom is bonded to each carbon. And then we can draw an alternating single and double bond pattern. So these two structures are in resonance. If a carbon-carbon single bond is 1.54 angstroms and a carbon-carbon double bond is 1.34 angstroms, but benzene is an average of single and double bonds, that means that the bond would be intermediate between single and double. So the average bond length for benzene, for carbons, would be not 1.34 or 1.54, but rather 1.44. Sort of 1.5 bonds is what we're talking about. So bond order is defined here. We have a bond order of either 1, 2, or 3 for single, double, and triple bonds. But if you have resonance forms, it's going to be an average. The bond order does not have to be an integer. It can be something like 1.5. On page 310, it says that the OO bonds in ozone are often described as 1.5 bonds. Is this description consistent with the idea of resonance? And the answer is yes. There are 2 resonance structures for ozone that each contribute equally to the overall description, so therefore the bond is an average of a single and a double, or 1.5. With nitrate, or carbonate, we have not 1.5 bonds, but rather 1 1/3. There are 3 resonance structures, each of which contributes, and so the 3 NO bonds is single, single, and double, and the average would be 1 1/3. So the bond order in ozone is 1.5. The bond order in something like SO3, which has 3 resonance structures, is 1 1/3. The carbon-oxygen bond in acetate is a 1.5. And as we said, nitrate, it's also 1 1/3. All right, moving on to section 8.7, exceptions to the octet rule. Each of these structures is going to have an odd number of electrons. So we have nitrogen monoxide, nitrogen dioxide, and chlorine dioxide. With an odd number of electrons, you just do the best you can without exceeding the octet rule. We have a situation where we have a single unpaired electron either on the nitrogen or on the chlorine atom. Other examples of exceptions to the octet rule would be when there is less than an octet. So boron bonded to 3 fluorines in boron trifluoride is only going to have 6 electrons around it. And you might think, well, why not just make a double bond? Well, it turns out that if you did that, it would be very unfavorable in terms of formal charge. So a BF double bond will give you a +1 formal charge on fluorine, and that is highly unlikely because of fluorine's strong electronegativity. So in this case, we'll go ahead and let the resonance structure that has a single bond with less than an octet is more favorable than making a boron-fluorine double bond. Now, boron fluoride can react with a molecule like NH3, and you get a molecule that looks like this. NH3 and BF3. The formal charge of nitrogen would be +1, and the formal charge of boron would be -1 in that particular molecule. Other exceptions to the octet rule are when you have more than an octet. These are called hypervalent molecules, and they're only going to happen for atoms from period 3 and below. If the central atom is in period 3 or below, then the reason why it can happen is because of the larger size of the central atom. So the molecules or ions that should exist are sulfur tetrafluoride, but not oxygen, because that's in period 2. Phosphorus pentafluoride, but not nitrogen. Again, that's also in period 2. Selenium hexafluoride, but not oxygen hexafluoride. Xenon difluoride. Iodine tetrafluoride with a charge of -1. And the tribromine ion that has a charge of -1. Let's go ahead and draw the Lewis electron dot structures for these 6 hypervalent molecules or ions. So sulfur tetrafluoride has a total of 34 electrons. There's an extra lone pair on the sulfur. Phosphorus pentafluoride has 5 bonds to fluorine. So again, another example of a hypervalent structure. It has a total of 40 electrons. In sulfur selenium hexafluoride, we have 48 electrons, and you would have a hypervalent structure. You could also have sulfur hexafluoride as well. Xenon difluoride has 22 electrons. There are extra lone pairs on the central xenon atom. In these two polyatomic ions, we have extra lone pairs of electrons on the central atom. So these are all examples of hypervalent structures. So now that we have an option of expanding the octet, let's go ahead and do that and talk about why that might be advantageous for us to do. So on the left, we have a molecule or an ion that obeys the octet rule. We have single bonds to phosphorus. And we have formal charges of -1 for each oxygen and +1 for phosphorus. So can we do better to minimize the formal charge on the atoms, even if it means having a hypervalent structure? Yes, we're still going to have -1s on 3 of the oxygens, but the central phosphorus now has a formal charge of 0, as well as one of the doubly bonded oxygens. So we've reduced formal charge, and we're allowed to have a hypervalent structure since phosphorus is in period 3. In a similar way, can we take a chlorate ion, which normally has formal charges of -1 and +2 when we obey the octet rule? Let's break the octet rule to form a hypervalent structure and try to minimize the formal charges. So look at that chlorine. There's 7 valence electrons minus 7 electrons assigned to that chlorine. So that chlorine has a formal charge of 0, and the doubly bonded oxygens also have formal charges of 0. So we are allowed to expand the octet because chlorine is in period 3. All right, moving on to the last section in Chapter 8, strengths of covalent bonds. The bond enthalpy is the energy required to break a particular bond in 1 mole of a gaseous substance. The greater the bond enthalpy, the stronger the bond. Breaking a bond is always an endothermic process, and forming a bond is always an exothermic process. So if we have a reaction involving nitrogen and fluorine to produce nitrogen trifluoride, let's use these bond enthalpies that are found on page 316 and the equation to estimate delta H. It's the sum of the bond enthalpies for all the bonds that are broken minus the sum of the bond enthalpies for all the bonds that are formed. So let's go find nitrogen. It's going to be a triple bond between nitrogen and diatomic nitrogen. Let's go find a single bond between the fluorines and a single bond between nitrogen and fluorine. So we need these numbers, 941, 155, and 272 to do our calculations. Let's go ahead and draw out the molecules. Again, just to kind of emphasize what bonds we are breaking. We are breaking a triple bond between nitrogen and a single bond between 3 fluorine molecules. We are forming 6 single bonds between nitrogen and fluorine. Let's go ahead and do the math. So we have a nitrogen bond, a triple bond, that's 941. We have 3 fluorine single bonds, that's 3 times 155. That's a grand total of 1,406 kilojoules, and that's positive because breaking a bond is an endothermic process. But we are forming 6 nitrogen-fluorine single bonds. That's a total of 1632, and that would be the energy released when those bonds are formed. So bonds broken minus bonds formed would be 1406 minus 1632, which means that the delta H is estimated to be negative 226 kilojoules for that reaction as written. Now we have another example of a reaction in which we have to use bond enthalpies to estimate delta H. We have C2H6, those are all single bonds. We have oxygen, diatomic oxygen, those are double bonds. We have carbon dioxide, which is a CO double bond. And we have water, those are all single bonds. So these are all the bonds we're breaking. We're breaking 2 carbon-carbon single bonds. we're breaking 12 CH single bonds, and we're breaking 7 oxygen double bonds. We are forming 8 carbon-oxygen double bonds, and we are forming 12 oxygen-hydrogen single bonds. So the numbers we need from table 8.4 are a CH single bond that comes in at 413 kilojoules. A carbon-carbon single bond is 348 kilojoules. We have the O2 double bond at 495. The carbon-oxygen double bond, which comes in at 799. And the oxygen-hydrogen single bond, which is 463. Let's use these numbers to do the math to calculate and estimate delta H. So we have 2 carbon-carbon single bonds, 12 carbon-hydrogen single bonds, and 7 oxygen-oxygen double bonds. Grand total of energy absorbed when bonds are broken, 9,117 kilojoules. So how much energy is released when the bonds are formed? Let's go ahead and calculate that. So 8 carbon-oxygen double bonds, 12 oxygen-hydrogen single bonds, grand total of energy released 11,948 kilojoules. If we put bonds broken minus bonds formed, we get a delta H of negative 2,831 kilojoules for that reaction as written. All right, we're almost done with the packet. The last question here in section 8.8 has to do with bond length and bond strength. In general, it says on page 319 that as the number of bonds between two atoms increases, the bond grows shorter and stronger. And this trend is illustrated in figure 8.17. And you can see that on the left we have a triple bond, which is short and has a high bond enthalpy. Then we go to a double bond, which is longer and has less enthalpy. And then finally a single bond, which is even longer and has even less energy. All right, well, that wraps up the information from the Chapter 8 packet. I hope that that was helpful to you. Good luck studying this material. Thanks for watching.